you've already taken, if you're taking physics or whatever like that, you're going to be a good help to us, and some of this might be a little bit of repetition of things you might hear. Hopefully we'll give a more, mathematical flavor to those ideas, though. So here's a graph of displacement of some object with respect to time, a dt graph, you might say. Sometimes we use, for distance, sometimes we use d, but maybe already you can see why d is maybe not a desirable letter for us. If we're using Leibniz notation, it'd be like dd, it would be confusing. So s is sometimes what we use for displacement, or x or y, or h if we're talking about height. We already have thought about these things, these ideas. Average velocity can be found by doing what? Well, average velocity is just average rate of change, right? So again, in the new context, I just want to make sure you're clear. By average velocity, we really just mean the same thing as before, slope of the secant. Change in position over change in time. So no big surprises here. No big surprises. This is still just slope formula from Algebra 1. The instantaneous velocity is a thing we care about as well. And of course, that's the slope of the tangent, or the derivative, right? Instead of delta s, delta t, it's ds dt, right? Just imagine those things becoming small as delta t tends to 0. You okay with that instead of h? Whatever. Something small. Yeah. Oh, it's a close one. It's a close one. All right. So this is us reframing everything we've been talking about for the last week or two in terms of velocity and position. So, good. Notice, of course, that the units come out in this calculation to be what? For this graph in particular? Yeah, miles divided by hours. So we might say that the velocity is the first derivative of position. I think maybe that's come out a little bit. I don't know that we've ever put it on the board or not. So there it is, in a box. Okay, there's a guy. And some of you, again, physics people were already, speed, you've heard people say, is the absolute value of the velocity, or you could say the magnitude of the velocity. So if anyone's talking about speed, you know what they mean. Okay, let's oh, that's a nice graphic, Mr. McDonald. Okay. So this is the free fall equation. We'll maybe think about where it came from more in a minute, but let's just take for granted that this is the free fall equation. You'll even see why soon, why that makes sense. And on Earth, at least, the constant g, which g is a constant, is 32 feet per second squared. If you're working in feet.
Why are we using feet, not meters?
All right, you can use meters if you like instead.
The world does meters. Why is
You can use 9.8
yeah.
if you like. All right, so simplifying that gives, for this particular situation, a position equation of this. So what do we mean? In the last context, we said, well, what do we mean by the velocity? Well, we mean literally the derivative of this position function. So if we're talking about this particular free fall equation, for example, and again, I just presented it here without too much understanding yet, then v of t, the velocity, will be the derivative of that, which is, of course, negative 32t. Any thoughts about that? Okay. Do you know Mr. McDonald is all about Mr. Have you guys said Mr. McDonald? You know he's big in the skydiving. 600, I think 600 time jumps.
What?
I think he logged 600 last year.
Yeah,
Yeah, he's a bro. He's got his motorcycle. He's a cool guy, right? Economics? Are you gonna take an economics?
He jumped out of the place.
It's like a hobby, you know, on the weekend. Beautiful day to be.
a lot of money.
Well, over the years. Over the years. It's a whole lifetime, right? I'm sure you get a discount. 7-year-old, 6-year-old process. All right, it's worth mentioning then, of course, that the acceleration, again, this is not maybe a huge moment for people in physics, but if we understand that acceleration by definition is the change in velocity, then the instantaneous change in velocity gives us the instantaneous change in acceleration. So we have our first application right now, if you hadn't thought of one yet, of a second derivative, right? A change in the change. So here I've written a is the acceleration function is dv dt, but it's also the second derivative of the position function, d squared s dt squared. So both boxes are needed here. For example, in our free fall equation, what's the very, very simple acceleration equation? All right, now I can finally, I gave that free fall equation without any understanding a minute ago, but I think maybe now you can understand that whatever the equation was, whatever equation we choose, should have the following property. When you take the derivative twice, you get a very simple acceleration function, negative 32, constant. Why? Well, because that's the assumption that all projectile motion in a vacuum has on Earth, is that we are all experiencing, all of us, a constant acceleration due to gravity on this planet, right? So that's the assumption, really, that maybe we start with, that Newton started with, and maybe you kind of work backwards to the other thing, right? And don't let's get very away with that, but you can see that whether you can think about where that came from or not, you can see that we've done it right, whatever that original free fall equation was. Whoever came up with it, this is what should happen if you take two derivatives. And then what are the units of that? Again, I said them a few minutes ago, but let's not gloss over them. What are the units? If distance is measured in feet, what are each of these measured in? Velocity will be, of course, feet per second, say, again. And acceleration will be what?
Feet per second squared.
Yeah, and feet per second squared is fine. So velocity is measured in feet per second, and acceleration is measured in feet per second, because that's what the velocity is, divided by one more unit of change for the seconds for the acceleration, right? So yeah, you do get feet per second squared because of like algebra, right? But in some senses, I think this actually still makes most sense intuitively, right? Like I think a lot of people have trouble understanding why that makes sense. Feet per second per second. That's a little weird for acceleration to be measured in that. Or feet per second squared. Like what's with the two time units? But it actually does make sense. In fact, let me give you a really weird unit of measure, which actually in the end will make very good sense to you. How about what would it mean for me to accelerate in my car at like 3 miles per hour per second? 3 miles per hour per second. Those are the two time units in there. That would mean I'm like starting at 50 miles per hour, and then I do what over the next second or two?
Each second you go 3 miles per hour faster.
Yeah, and then I think we can all picture that. We can even feel it in the car, what I would be doing if you were with me in the car. We could, we start at 50 miles per hour, and if I were to accelerate 3 miles per hour per second, a second later, maybe I'm going 53 miles per hour. And then a second after that, 56 miles per hour if I was at a constant acceleration. That makes sense. So here, this makes good sense too. What does that mean? As you drop an object, free fall, say, every second, what happens? Its acceleration stays the same. What about its velocity? It increases if you depending on which sign you have, but it goes from being 0 velocity, if it's free fall, say, you just drop it, we don't give it any initial velocity. But then a second later, it should be going 32 feet per second. And then a second later, it should be going 64 feet per second. Do you understand now what 32 feet per second means? Every second, the velocity adds 32 feet per second to it, right? So I just want to make sure you're clear on that, because I know that's sometimes a theoretical sticking point for people, yeah.
And the sign just refers to the direction of velocity, correct?
Yeah, in this particular case, later in the year, we will consider velocity like a full-on vector when we do, and we'll have it be some vector in 2 dimensions or something. But here, our velocity will always be a signed number, which will represent either like left or right, or up or down or something. Positive or negative number of some kind. What else was I going to say about that? I don't know. Feet per second per second. I hope that makes sense to you. The velocity function, does this make sense? Now let's go back to the functions themselves here. The acceleration function is always negative 32 feet per second squared. Does it make sense that this would be the velocity function? now? Yeah.
Yes.
It does, because every second the velocity is going up, or if you have it signed in the way, S-I-D-N, signed in the way I have it here, it's going down, I guess, by 32 feet per second. More. Yeah. You don't know the answer? Yeah, does anyone know? They're fun. Yeah. Jerk is the next acceleration, so I think I've even seen someone nerdy walking around in this school, maybe even with that. Don't be, and then Leibniz notation, d3 x dt, or whatever, dt to the third, right? The third derivative of position. Don't be a jerk, you know. Which makes sense, because isn't that what you intuitively feel like the change in acceleration is? Right? Like, please, Father, as you drive the car, please accelerate linearly, you know, like can you control the third derivative a little bit, you know? Anyway, and then do you know what the fourth, fifth, and sixth derivatives are called? Yeah, snap, crackle, and pop. And then I think they have other names for other ones. Google it. No one needs to talk about that though, but it's fun. And physicists have a good sense of humor. I mean, they're also the ones who named all the forks, right?
Oh yeah.
Right? They just like to be funny. Jerk actually makes sense. They're not trying to be like, you know, that actually makes sense. Jerk, as in like changing the acceleration. Snap, crackle, and pop. They're just like it's funny. But no one needs to think about those. All right, let's take a look at Let's take a look at this graph, and I want you to think if this is a distance time graph. I want you to think not just about what's happening with the distance, though you can answer that. I want you to think about at each point along this curve. I'll highlight different intervals. I want you to think about what's happening with the velocity and acceleration of this moving object. Okay, so for example, in this first interval, how about from here to here? What's going on? First of all, let's say we've got a motion sensor or something like that. I'm walking away from a motion sensor, say. Okay. Looks like over time I'm going away from the motion sensor and then I'm coming back. Okay, that's what's happening with the distance. So, but on this interval, what's happening with the velocity? Yeah, velocity is increasing. It's also, let's back it down one notch. It's also, velocity has what sign? Positive. Yeah. So it's both velocity is positive and velocity is increasing. It looks like not only is it positive, but it's also getting more positive, right? So I'll say that here. Acceleration is positive and the velocity is positive, and the distance is increasing. Acceleration is positive because velocity is increasing, right? There are a lot of things to keep track of that are changing. All right, what about the next interval? Let's go from here to here now. Let's say it's like a linear between there. Let's say that's just a line. I don't know why. It wouldn't be necessarily, let's just say it is. Yeah. Yeah, what would you say, what's happening there? So let's talk about velocity and acceleration.
Velocity is constant, that means there's no acceleration in that period. So acceleration would be 0 and velocity would be positive.
Yeah, velocity would be positive and constant, right? Yeah. So the acceleration, though, is 0. If it really is true that the velocity is some constant number, then the slope of this graph always has the same answer, right? The slope of the graph isn't changing. The velocity is not changing. It's 0. The acceleration is 0. All right, and then what about this interval up to the peak here, from here to here, say? Who wants that? Okay, tell me about the velocity and the acceleration. I'll say both. Right.
The velocity is increasing, the deceleration is decreasing because the velocity is increasing, it's decreasing the rate.
Careful, we're not talking about speed here. Keep in mind. The velocity is positive.
The velocity is positive, but the velocity is decreasing.
Good. See, it's hard.
The
This is
position is increasing and it's decreasing.
okay. Fine. Yes. All the things you said are now okay. Yeah, the acceleration here is negative. It's hard to think when you look at that graph that there's anything negative about this movement. But yeah, our velocity is decreasing as we go from here to here. You can calculate slopes of tangent lines along the curve and see that that's the case. Velocity here is like 2, and then it's like 1, and then a half, and then it's getting closer and closer to, well, what? Up at the top point there. Yeah, up at the top there, the velocity is 0. So what happens on the next interval? Take that one. Go ahead.
The acceleration is negative, the velocity is negative, and decrease.
Yes, I think you said all that, right? Yeah, here now finally we're at a place where the velocity is negative. And the acceleration is still negative. And then what about, let's pretend that's constant. So what would, or excuse me, that's a linear piece of the distance function. Someone answer that one, Julie. Go ahead.
Velocity is negative and the acceleration is 0.
Good.
And velocity is constant.
Yeah. And then what about this piece right here? We'll go to here. You want to take that, son? Is that you, Isha? Go ahead. Go ahead.
Oh, okay. So, from
I know you didn't know.
that's okay. So in that interval, your velocity is decreasing and your acceleration is negative, so you're slowing down.
It is.
They'll just be coming less night.
Amy.
The velocity is still negative because it's still downward.
Yeah, the velocity is still negative. Does everyone agree with that? Like
And then-
any slope you calculate along here will be negative.
The acceleration is becoming positive because even though it's only flat, like becoming flat, the velocity is going from negative to 0, which is still increasing.
Yeah, it's hard to see that the acceleration is positive here, but it is. Again, if you have any doubt about that, start actually calculating slopes. Here, it's like -3 or something, and then -2, and then -1, and then -0.5. Is the velocity actually increasing along here? Yes, it is. Therefore, on that interval, the acceleration is a positive number. And then maybe down here, we level off, maybe say, there the acceleration would be 0 again, and the velocity would be 0. We stay the same distance from the motion detector, say, just stand there. So lots going on that we can discuss, even a simple curve that we just sketched. All right, so we've got not very much information to go on here, but this is really, there's only one number in this problem. In November of 1959, Kilauea Iki erupted in Hawaii. And the only number given in this problem, 1,900 feet straight into the air, is how high the particles of lava flew. So, again, I'm handing you this position equation, but maybe eventually you'd be able to derive it yourself, where V0 is the exit velocity. Find that velocity. Not a lot to go on here, right? But maybe it's enough to say what we need to say. We know that the velocity is this function. Take the derivative, right? So that's what I have in front of you. Do you agree that that's the velocity function we're looking for? Still don't know what V0 is. Still don't know what V0 is. But what did we say is true about that point where it reaches its highest? Yeah. What she said? Yeah, the velocity is 0. So we could find that time right now, couldn't we? By setting the velocity equal to 0. So what time do we get? We get t equals V0, whatever V0 is, divided by 32. Good. We now know when it peaks. Well, now the original equation is of use to us. We still haven't even used the 1900, have we? So, let's go back to the original equation. What can we make? What substitutions can we make? Yeah, this is t in both places. And what will the position s be? 1900. And that's an equation that has only one unknown variable, v0. Solving that. Gives the gives the result. So you can see that just really, really simple thinking about derivatives helps us get a long way into thinking about physics. And in some ways, well, in every way. Like all you need is math in life. You know, you don't need really a physics class. You just need to know calculus, right? I had in mind to do this. Maybe we'll work on this a little bit right now for a couple minutes, and then we'll figure out what this tomorrow a little bit. So we won't have time to talk as well. The homework tonight will be homework 5, but we can at least start with 6. If you multiply the first fraction by 16/32.
Wait, is homework number 6 also?
Yeah, let's do homework 6 for homework tonight. This is I thought I'd have a few minutes to get this started here as well. So we can work on this for a minute if you like, but we'll just don't lose it, and we'll pick up with it tomorrow if you like too. So, because I do think there's some useful things to talk about on here. In particular, what on here it says, yeah, there are definitely some things we still need to maybe discuss, but I think you're fine doing homework tonight. We keep this around, and we'll look at it some more tomorrow. Yeah, the homework is homework 6 from the book. Just to make sure that's clear. Homework 6 from the book is what I will check tomorrow.